Hello Year 9, I'm going to talk you through your analysis and solubilities test and hopefully help iron out any problems you might have had in order to be able to make sure you know what you're doing before your exams after half term. So I'll talk you through each of the questions and bits and pieces that you might need a bit of extra support with. I'll talk you through how to do those as well. Okay, so question 1, we've got compound X, we're adding sodium hydroxide to it and we're getting a red-brown precipitate. That is just a question that needs you to have learnt your analysis. So you need to know that red-brown precipitate with sodium hydroxide means that we have Fe3+ ions present. Number 2, dilute nitric acid added to a solution of compound X and no effervescence. So what kind of things might we expect to fizz with acid? When we're thinking about ions here, that would be our carbonate ions. So if there was no effervescence, that simply means that it's not a carbonate ion. You might have listed what it could be. So of other negative ions you could have, it could be a halide or a sulfate. And if you've put that instead, you need to say both of those. Next one, we've got barium chloride solution being added and there's no change. So again, this involves learning our tests. We need to remember that barium chloride tests for sulfate ions. So if there was no change, then that means it's not a sulfate ion. So our last test there, we've got silver nitrate solution being added to a solution of compound X, and that gave us a white precipitate. We need to know that silver nitrate is testing for halide ions. That means our ones that come from the halogens, so our group 7, chloride, bromide and iodide. And you need to learn that the white precipitate one means we have chloride ions there. Okay, so we then need to fill in our deductions in the table. So the name of compound X. So we have got iron 3 ions and we've got chloride ions. So our compound is going to be iron chloride, but we can be more specific than that. So we can say we have got iron 3 in Roman numerals, chloride. And that tells us, when it's written down, that we've got the iron 3+ ions in there as opposed to the iron 2+. So you get 1 mark for saying iron chloride, but your second mark for the full marks on that question comes from saying the iron 3 chloride. Then we need to give the formula of our compound. So thinking about the charges on the ions that we've got, I'll put a bit of working up here the way I like to do these. So we've got Fe3+ ions and we've got Cl- ions. 3 positive charges, 1 negative charge. So we need 2 more of the negative charges in order to counterbalance it. With now 3 negatives, 3 positives, so we've got everything we need. And we write that down, FeCl little 3 down at the bottom. So that's iron 3 chloride. Okay, now if D test 2 is still showing on your sheet, we scrapped that one in the end because there was a little bit of confusion with the numbers. It should really have been for test 1 because there was no change in test 2, so you can't write the ionic equation. Now the other one did refer to test 5 initially, I'm aware of that, but it was changed fairly quickly to be test 4, and in any case it was obviously going to be the last test if there was no test 5 present. So I'll give you the answer for that, but we'll think through how we come to it first of all. So we've added silver nitrate. I'll do a bit of working down here actually. We've added silver nitrate. And one of the things you need to learn with your solubilities is that all nitrates are soluble. So we know that's aqueous. And we've decided that we've got chloride ions present. So it must have reacted with the chloride ions to give us our white precipitate. And they were in solution. It tells you that in the question. Then we need to think what our compound is going to be on our other side. So we've got a positive silver ions would pick up the chloride ions, forming that white precipitate of silver chloride. And then I suppose if you're doing it the way I'm doing it here, then you would need to put some nitrate ions over there. But that isn't your ionic equation. The ionic equation always contains the ions that have changed. So nitrate's always aqueous, so it's over there. So what we need to spot here is the ions that have changed. So everything was aqueous on the left, nitrate is still aqueous on the right, but the silver chloride is now a solid. So that contains ions that have changed from being aqueous to a solid. So they're now locked together. So the ions that have changed are all here now. So to balance our equation, we need to have those ions on the left-hand side. So silver ions, which originally were aqueous in our silver nitrate, plus chloride ions, aqueous from our solution X in the first place, is going to react to form silver chloride. Okay, so that's what you should have in that box. In terms of the bits down here that were to help your teachers with their marking, left-hand side, right-hand side and state symbols. So if any of those are highlighted, that's where you have lost marks. Okay, so you need to check your left-hand side looks like this, your right-hand side looks like this, and that you've got all the correct state symbols there as well. Okay, over to the other side here. So let me just get you back in focus. This is very technical. We've got a camera held on a little mini tripod thing here. You might have one of those at home. Okay, describe carefully what test you would have to carry out to identify the ammonium ion in an unknown compound. This is just a learning question. Okay, so you need to add sodium hydroxide. You need to warm. And when you react ammonium ions with hydroxide ions, you produce ammonia, and that is an alkaline gas. So we then need to test the gas with damp pink litmus. It's always damp because otherwise the gas won't actually interact with the litmus paper. If it's damp, it will dissolve in the water a little bit. And the litmus is going to turn blue. So each of those bits is going to give you a mark there. Then we can have the equation. It doesn't matter here if you choose to write the ionic equation or the overall one. I'd say the ionic is probably easier. So we have got ammonium ions, which were aqueous, and they were reacting with hydroxide ions, aqueous. And have a look at what we've got. So we talked before about the fact we're going to get that ammonia, the alkaline gas produced. So that's NH3 gas. Then if you can't remember what the rest of the equation looks like, do a bit of spotting the difference. So we've used 1N, so 1N over there, 3 H's on the right, and we've got 5 H's on the left. So we need 2 to appear on the right in a minute. 1 O on the left, none of them on the right. It's a common molecule that contains 2 H's and an O, and that's got our H2O, which will be a liquid. Okay, marking similar to before, so we've got 1 for the left, 1 for the right, and 1 for the balancing in this case. So actually there's no mark for the state symbols. So if you've put them on the wrong, it doesn't matter. If you put them in the right, brilliant, that's handy. Next one then, more learning of how to do our tests. So for our compounds here, we need to tell the difference between sodium chloride and potassium chloride. So we're telling the difference between something containing sodium ions and potassium ions. Now, adding sodium hydroxide, if you remember doing the test with that, it identifies lots of cations, but there's no change with sodium and potassium compounds because all sodium and potassium compounds are soluble, so you'd never get precipitate. So we need our flame test here. So key points when you're writing a method for the flame test. Well, first of all, how would we carry it out? So let's identify that we're going to do a flame test. And then we need to think about the method steps. So we need to clean the flame test wire. We're going to dip it in the sample. I've missed out a few words, you know what I mean? And then we're going to put it in the Bunsen flame. Don't say you are going to burn it because we're not burning it. We're actually just applying enough heat to excite the electrons in the structure there and allow them to change energy level, which allows them to give out the light, but we're not burning it. So we then need to say what we're going to see. So sodium chloride, sodium ions, you should have learnt give a yellow flame, and potassium chloride, you should have learnt the potassium ions give that nice lilac flame. Okay. Right, compound Y. So it's again, what does these tests tell us about our compound? So we have got sodium hydroxide solution being added to a compound Y, and in this case we're told that we've got aluminium sulfate, so we need to remember what we would see with each of these. So sodium hydroxide with aluminium ions, we get a white precipitate, but what you need to remember is that it redissolves in excess. Okay, it's my shorthand for the word excess, right, excess. Okay, and that helps us distinguish between aluminium ions and calcium ions, because they would both give you a white precipitate, but the calcium ions, the precipitate doesn't dissolve. Nitric acid doesn't have any effect on aluminium ions or sulfate ions, so we can say no reaction. And then barium chloride. So we mentioned barium chloride before being a test for sulfate ions, and then you have to know that when you test for the sulfate ions you get a white precipitate. So your 4 marks here: white precipitate and redissolves, and then no reaction and white precipitate. When it comes to the ones where there's no reaction, always state no reaction, because if you leave it blank it doesn't show that you know that there was no reaction. It could mean that you just missed it out. Okay, so let's go on to the next bit. So let me carry you over to the top of this one. Okay, so in this question we have got some data from a flame photometer, and it says that that's going to be used to determine the concentration of ions in dilute solution. So diagram above shows a calibration curve. We want to deduce the concentration of potassium ions that give us a reading of 25%. So make sure you've got a ruler, no wonky lines here, and then you need to find 25%. You need to draw a horizontal line across that way, and then you need to match it up with a vertical line down there, and then you need to read off. Okay, so your teacher will have checked where your lines are, so that you can show what you're doing there, and you should end up with a value of 0.0. It will be between 0.04 and 0.05 along there. Okay, so there's a little bit leeway there. So 0.045 is what we're aiming for, really. Sorry, hang on, wait a minute. 0.044 and 0.45. Apologies there, I've missed out a number. Okay, so I hope you can see that written in there. Okay, in the next question then, so the flame emission spectrum for the sample here. Use the spectrum provided to determine which element could not be present in our sample. So we have our unknown sample, and then we've got all these elements, and this is just to spot the difference. So have a look across each of these and see which set of lines just don't appear in the top. Okay, and probably very clearly that's going to look like A. So we can see this one down here, that features here, that one's up there, that one's up there, and so on. Okay, so that one is going to be A. Then it says the spectral line below 400 nanometers and at 550 nanometers were brighter than the others. Use the data to explain what this suggests about the composition of the sample. Okay, so if we have a look at which element those lines are going to correspond to, you might need to look at your version to see the numbers better here. So below 400, so if I just draw on, that's 400. And at 550, so that's here, they were brighter. So the only one that has got a line bang on 550, that's that line there, and below this 400 is that one there. So we're talking about element B. So the lines correspond to element B, and if the lines are going to be brighter, that's because we've got a higher concentration. So we can say then that the lines tell us we're talking about element B and higher concentration, so we can say, higher intensity, so must be a higher concentration. Okay. Right, up onto the other side here. Okay, so we have got a next question about insoluble salts made by precipitations. So name the precipitate formed during the reaction between lead nitrate and potassium bromide. So when we do this, remember that basically we swap over the ions. So lead originally came with nitrate, so lead could end up with bromide, and the potassium and the nitrate could end up together. Then we need to think about what we know about solubilities. Okay, one of these two must be insoluble because the question obviously implies we're going to get a precipitate. And shortcuts to learning solubilities is learning that all sodium and potassium compounds are soluble, all nitrates are soluble, and all ammonium compounds are soluble. And that actually covers quite a lot of things and it's quite useful. So from those little simple bits alone, lead and bromide ions don't feature up there, so we don't really know about them at the moment. But potassium nitrate, they both feature in there. So even if you only had one of those, it would definitely be soluble. So our potassium nitrate is soluble, so our lead bromide must be insoluble, and if it's insoluble, it's the precipitate. Okay, so that is lead bromide. And remember, a precipitate, the definition of that would be the solid formed by the reaction of two solutions. So we want a balanced symbol equation with state symbols now for that reaction. So that needs us to make sure we're thinking about charges on ions. So lead nitrate, you need to remember that lead ions are 2+ and nitrate ions are 1-. And so our lead nitrate will be PbNO3 twice. Remember, if we want more than one of an ion that contains more than one thing, like our nitrate here, we must put in brackets. Otherwise you'd have 32, which doesn't make any sense. Okay, it's going to be reacting with potassium bromide. So we've got K+ and Br-, so that's KBr. And then we need to work out our products. So we were forming lead bromide, so that's going to be PbBr2 from the 2+, 1-, and potassium nitrate, so KNO3. Balancing, 2 Brs there, so we need 2 of those, 2 Ks here, so we need 2 of those, 2 nitrates, 2 nitrates. State symbols, nitrates were soluble, potassium compounds were soluble. We already identified that as our precipitate, and nitrates are soluble again there. Oops, gone off screen again. Okay. Then the next one, an ionic equation. So we want an ionic equation when we've got this precipitation reaction. Aqueous, 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 solid. So this contains the ions that have changed because the rest of them were aqueous at the beginning and the aqueous at the end. So all we need to do is pluck that apart and put the ions on the left. So barium sulfate, barium ions, Ba2+, and sulfate, so we want sulfate ions. It's a good idea to think in terms of the name because it avoids you trying to pluck things apart into things that weren't ions there in the first place. Okay, so barium sulfate, barium ions, and sulfate ions. Our two soluble compounds. Now, if we want to form copper carbonate, we need to start with a copper something and a something carbonate. Okay, now we said that all nitrates were soluble, so if you choose copper nitrate, that's definitely soluble. And we said all sodium and potassium compounds were soluble, so if we choose, say, sodium carbonate, it's definitely soluble. You might have other ideas down there as well, but your teacher will have checked those. Okay, last question then. We've got our copper carbonate. It's insoluble. How do we get it out of there? Simply filter, rinse,